Welcome to today's paper reading. Today's paper is titled, Ring Attention with Blockwise Transformers for Near-Infinite Context. This paper was published as a preprint by Hao Liu and colleagues from UC Berkeley. The abstract highlights the challenges posed by transformers' high memory demands, particularly in handling long sequences. To address these issues, the authors introduce ring attention, a novel approach that uses blockwise computation and distributed processing across multiple devices. This method allows for the training and inference of sequences that are significantly longer than what was previously possible, without the need for approximations or additional computational overhead. The effectiveness of this approach is demonstrated through extensive experiments in language modeling and reinforcement learning tasks, showing improvements in performance and the ability to handle larger context sizes. Transformers, the backbone of many state-of-the-art AI systems, utilize self-attention and position-wise feed-forward mechanisms to achieve impressive performance. However, scaling the context length of transformers is challenging due to the quadratic memory cost in the input sequence length. Research has focused on reducing this memory cost through blockwise computation of self-attention and feed-forward networks. Despite these efforts, storing the output of each layer remains a significant challenge. This necessity arises from the inherent nature of self-attention, which involves interactions among all elements. Scaling context length is essential for processing long sequences, such as books, high-resolution images, and complex code bases. The memory demand for such tasks is substantial, often exceeding the capacity of contemporary GPUs and TPUs. Figure 1 illustrates the maximum context length achievable during end-to-end large-scale training on TPU v4-1024. The baselines include vanilla transformers, memory-efficient transformers, and memory-efficient attention and feed-forward, blockwise parallel transformers. Our proposed ring attention approach allows for training sequences that are up to the number of devices times longer than the baselines. This is achieved without making any approximations or adding any additional overheads to communication and computation. This capability enables the training of sequences that exceed millions in length, significantly enhancing the scalability and efficiency of the training process. The attention mechanism in transformers involves computing the attention matrix using queries Q, keys K, and values V. This is done through a softmax function applied row-wise to the scaled dot product of Q and K, followed by a multiplication with V. Each self-attention sublayer is accompanied by a feed-forward network, which consists of two linear transformations with a ReLU activation in between. Recent advancements, such as blockwise parallel transformers, BPT, have significantly reduced memory usage by computing attention in a blockwise manner. This approach limits the maximum activation size of the feed-forward network, contributing to more efficient memory management in transformers. The primary objective of this research is to eliminate memory constraints on individual devices by efficiently distributing long sequences across multiple hosts without adding overhead. To achieve this, the authors propose an enhancement to the blockwise parallel transformers (BPT) framework. When distributing an input sequence across different hosts, each host is responsible for running one element of the outer loop of blockwise attention corresponding to its designated block, as well as the feed-forward network specific to that block. These operations do not necessitate communication with other hosts. However, a challenge arises in the inner loop, which involves key-value block interactions that require fetching blocks from other hosts. To tackle this challenge, the authors leverage the permutation invariance property of the inner loop's key-value block operations. This property allows the self-attention between a query block and a group of key-value blocks to be computed in any order, as long as the statistics of each block are combined correctly for rescaling. The authors conceptualize all hosts as forming a ring structure, where each host efficiently coordinates by concurrently sending key-value blocks being used for attention computation to the next host while receiving key-value blocks from the preceding host, effectively overlapping transferring of blocks with blockwise computation. This overlapping mechanism applies to both forward and backward passes of the approach, since the same operations and techniques can be used. The authors also determine the minimal required block size to overlap transferring with computation, which should be greater than or equal to the ratio of flops over bandwidth. Figure 2 illustrates the ring attention with blockwise parallel transformers, ring attention, approach. In Part A, the diagram shows a ring of hosts where each host holds one query block, and key-value blocks traverse through the ring for attention and feed-forward computations in a block-by-block fashion. During this process, each host sends key-value blocks to the next host while receiving key-value blocks from the preceding host, effectively overlapping communication with computation. Part B visualizes the original transformer block-by-block computation, where each host is responsible for one iteration of the query's outer loop, and key-value blocks rotate among the hosts. The query block, combined with the key-value blocks, computes self-attention, and the output is passed to the feed-forward network. Table 1 provides a detailed comparison of the maximum activation sizes among various transformer architectures. The vanilla transformer architecture shows a self-attention activation size of 2 BNS superscript 2. In contrast, the memory-efficient attention architecture reduces this to 2 BSH for self-attention. Our proposed ring attention method further optimizes this, with a total activation size of 6 BCH, demonstrating linear memory scaling with respect to the block size C and independence from the input sequence length S. This comparison highlights the efficiency gains of our approach in managing memory requirements for transformer models. Table 2 outlines the minimal sequence length required for each device, considering the interconnect bandwidth between hosts, such as NVLink, InfiniBand for GPUs, and ICI for TPUs. The table highlights that the minimal block size required is determined by the ratio of flops to bandwidth, C equals flops/bandwidth, and the minimal sequence length is 6 times this block size, S equals 6C. This information is crucial for optimizing the performance of transformer models across different hardware configurations. In this study, the authors evaluate the impact of ring attention on transformer models using the Llama architecture with model sizes ranging from 3B to 30B. They apply full gradient checkpointing to both attention and feed-forward networks, following established practices. The baselines for comparison include vanilla transformers, transformers with memory-efficient attention, and those with both memory-efficient attention and feed-forward networks. The training configuration involves experiments on both GPUs and TPUs, including single and distributed GPU setups, as well as TPU generations from TPU-v3 to TPU-v5e. Notably, all results are obtained using full precision. In evaluating the performance of ring attention, we focus on 3 key areas: maximum context size, model flops utilization, and in-context reinforcement learning performance. For maximum context size, we use fully sharded data parallelism, FSDP, to ensure a fair comparison. Ring attention significantly extends the sequence length, enabling a much larger context size. In terms of model flops utilization, NFU, we assess the impact of model size and context length. Ring attention results in higher self-attention flops, which is expected due to its design. Lastly, in the context of reinforcement learning, ring attention improves performance on XORL tasks by scaling the sequence length, leading to better cumulative returns. Table 3 presents the maximum context length supported in end-to-end training using fully sharded data parallelism across various transformer architectures and hardware configurations. The baselines include vanilla transformer, transformer with memory-efficient attention, and transformer with both memory-efficient attention and feed-forward. The context size is reported in tokens, 1 times 10 cubed. The results show that ring attention significantly outperforms these baselines, enabling training sequences that are up to device count times longer than the prior state-of-the-art. This demonstrates the superior scalability of ring attention across diverse hardware setups, with improvements scaling linearly with the number of devices. Table 4 illustrates the model flops utilization, MFU, across various training configurations, including different model sizes, compute resources, and context lengths. The table highlights that ring attention facilitates the training of large models ranging from 7B to 65B on extensive input context sizes exceeding 4 million tokens with minimal overhead. This approach maintains high MFU while significantly extending the context lengths, as evidenced by the configurations using 8xa100 GPUs, 32xa100 GPUs, and TPUv4-1024. The context sizes range from 8 to 2048 times 1e3, showcasing the scalability and efficiency of ring attention in handling large-scale model training. Table 5 illustrates the application of ring attention in improving transformer models for reinforcement learning (RL). The table compares different models, including behavior cloning (BC), decision transformer (DT), and augmented transformer (AT), with various attention mechanisms. Notably, AT with ring attention, AT plus RA, consistently outperforms AT with blockwise parallel transformer, AT plus BPT, across 6 tasks in the XORL benchmark. The total average return for AT plus RA is 113.66, compared to 111.13 for AT plus BPT. This demonstrates the advantage of ring attention in enabling the training and inference of longer sequences, which is crucial for RL tasks involving extensive trajectory data. Figure 3 illustrates the performance of various models on the long-range line retrieval task, which assesses the ability to accurately retrieve information from lengthy documents. The ring attention 13B512K model demonstrates superior accuracy even with extended context lengths, highlighting its effectiveness in managing long sequences. In contrast, models like GPT 3.5 Turbo 16K, the CUNA 16B16K, and Claude 2-100K show competitive accuracy within shorter contexts but struggle with longer ones. This comparison underscores the advantage of ring attention in handling extensive textual data, making it a robust choice for tasks requiring deep contextual understanding and precise information retrieval. Transformers have been extensively studied for memory efficiency. Techniques such as the tiling method have been used to develop memory-efficient attention mechanisms. Various parallelism methods like data, tensor, and pipeline parallelism have also been explored. However, sequence parallelism introduces significant communication overheads. Our approach addresses these challenges by fully overlapping communication with blockwise computation, enhancing scalability. The authors propose a memory-efficient approach for transformers, which are the backbone of state-of-the-art AI models. This approach allows the context length to scale linearly with the number of devices while maintaining performance, thus eliminating the memory bottleneck imposed by individual devices. Extensive experiments on language modeling and reinforcement learning demonstrate its effectiveness, enabling training sequences that are up to device count times longer than those of prior memory-efficient transformers, exceeding a context length of 100 million without making approximations to attention. The possibility of near-infinite context introduces a vast array of exciting opportunities, such as large video-audio language models, learning from extended feedback and trial and errors, understanding and generating codebase, adapting AI models to understand scientific data such as gene sequences, and developing strong reasoning from link-gathering data. This project has been partially supported by the Office of Naval Research through grant number N00014-21-1-2769. The authors would like to express their gratitude to the BEAR and RLL communities for their valuable discussions and feedback. Special thanks go to David Patterson for addressing questions about TPUs and providing insightful feedback on early versions of this work. The authors also appreciate the assistance of Yash Kataria and Sharad Vikram from the JAX developers team in answering their JAX-related queries. Additionally, they thank TriDAO for his valuable feedback on this work. Access to TPUs was granted by the Google TPU Research Cloud, for which the authors are also grateful. Thank you for watching.